All right, this is Advent of Code, day 22 in OCaml in 3, 2, 1, go. Day 22, monkey map. The monkeys take you on a surprisingly easy trail through the jungle. They're even going in roughly the right direction according to your handheld device's grove positioning system. As you walk, the monkeys explain that the grove is protected by a force field. To pass through the force field, you have to enter a password. Doing so involves tracing a specific path on a strangely shaped board. At least you're pretty sure that's what you have to do. The elephants aren't exactly fluent in monkey. The monkeys give you notes that they took when they last saw the password entered, your puzzle input. The first half of the monkey's notes is a map of the board. It is comprised of a set of open tiles on which you can move, drawn dot, and solid walls, with tiles which you cannot enter, drawn pound. The second half is a description of the path you must follow. It consists of alternating numbers and letters. A number indicates the number of tiles to move in the direction you are facing. If you run into a wall, you stop moving forward and continue with the next instruction. A letter indicates whether to turn 90 degrees clockwise or counterclockwise. Turning happens in place. It does not change your current tile. So a path like 10R5 means go forward 10 tiles, then turn clockwise 90 degrees, then go forward 5 tiles. You begin the path in the leftmost open tile in the top row of tiles. Initially, you are facing to the right from the perspective of how the map is drawn. If a movement instruction would take you off of the map, you wrap around to the other side of the board. In other words, if your next tile is off the board, you should instead look in the direction opposite of your current facing as far as you can until you find the opposite edge of the board, then reappear there. For example, if you are at A and facing to the right, the tile in front of you is marked B. If you are at C and facing down, the tile in front of you is marked D. It is possible for the next tile after wrapping around to be a wall. This still counts as there being a wall in front of you, and so movement stops before you actually wrap to the other side of the board. By drawing the last facing you had with an arrow on each tile, the full path taken by the above example looks like this. To finish providing your password in the strange input device, you need to determine numbers for your final row, column, and facing as your final position appears from the perspective of the original map. Rows start from 1 at the top and count downward. Columns start from 1 at the left and count rightward. In the above example, whatever. The final password is the sum of 1,000 times the row, 4 times the column, and the facing. What is the final password? Okay. Yikes. How big is this map? Okay, very big. Got it. Oh my God. I can see why this one takes a while. Okay. Let parse input equals all right, string.subster replace all input pattern with let maze path equal in util let maze grid dot of puzzle input maze f module square type t equals open wall and void. Open wall or wrap. Fun ch function square dot wrap deriving sex compare hash. All open. Tail width invalid maze car. In let parse path equals let module path lm path lm struct type t equals move of int left counter clockwise equals let replace equals input path L with string that strip this.map fun s function L path lm dot counterclockwise path lm dot move int dot of string s. Maze parse path. Phase path equals path lm dot t list. Print f at 0, 0. December 22nd dot input. Uh, 10, 0, and 0, 7. Square dot to string of grid dot L split 2. Excellent. There we go. Ten, 0. Oh no, they're not the same. Let parse maze input equals let max length equals list max lengths in parse maze so let's do 11. And 8. Do do do. Lines. And line. Oh. Okay, well, stupid mistake one. nothing, 11 0 pound dot 8. Great. So we have move 10 clockwise, move 5 counterclockwise, move 5 clockwise, move 10 counterclockwise, move 4 clockwise, move 5 counterclockwise, move 5. Okay. Let starting spot maze equals leftmost open tile in the top row of tiles. Let y grid dot width let starting x equals ref none in for x equals 0 to grid dot width maze -1 do 0 match if option dot is none starting x match starting x grid maze x with none square dot open starting x x let sx y equals find starting spot maze. For list you are facing to the right. Let dx equals 1 0 in iter path do path fun p match p with let rotate t dy match t dx dy with move, fail with, can't, rotate, move. Counterclockwise, 1, 0. Zero, -1, -1, 0. Fail with, invalid, dx dy. So if you're going right, then okay, I need to remember y is flipped. So if you're facing right, then module dir type t equals right, left, right, down, left, up. Dir. Let 2 dx dy equals a function right, down, left, up. Dir dot right. Right, up, down, counterclockwise, dir dot up, left, dir dot down, left, dir dot right. Up, dir dot right. Dir. Move n. Let pause equals move n steps maze pause dir. Let move n steps maze pause, dir. Counter path counterclockwise, dir. Path elm.rotate. P, dir. In. Ouch. Do 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 do. Module point equals struct x int y int. Let create xy equals x y. Point dot create. Last facing equals hash table dot create module point in. Oh. Let row equals pause dot y plus 1 in. let facing value zero right down, 0 right, 1 down, 2 left, 3 up, right down, 2 left, 3 up. Let facing equals dir dot facing value dir. Final password equals um, (1,000) times row, 4 times column. Okay, so for I equals 1 to n, do. Done. Okay, let first in row last in row. Okay. Let first non-empty sx, sy, dx, dy. Let sx equals sx in ref. In for d equals 1 in 1 to length do Oh. First equals first.x. First equals option.value xn first in. Let x equals match first y with none. Yes, these will always be. All or none square dot open. First non empty maze, first in row, x is -1, y row, dx, dy, let dx dy equals dir dot x dy dir in. Grid dot width maze grid dot width maze left. Down, call x, y, grid dot height maze up. let next in dir maze pause dir next in dir equals let x y pause in let dx dy equals dir dot to dx dy dir in let x equals x plus dx, let y equals y plus dy, and match if grid dot in range maze x y then if it's in range, else match dir with dir dot right, then find first in row maze y. Left first in call is x, oops, left match maze dot x with square dot wrap let wrap equals in Okay. Let next pause equals point.x, y equals next in dir maze pause dir in match grid.x maze with open wall wrap fail with next ender shouldn't be wrap. Then pause next printf moved to wise printf now facing up left. Printf now facing Oh my god. Move end steps. Ref, pause. There we go. Oh no. Let's go. Part 2. As you reach the force field, you think you hear some elves in the distance. Perhaps they've already arrived. You approach the strange input device, but it isn't quite what the monkeys drew in their notes. Instead, you are met with a large... Oh my god. Each of its 6 faces is a square of 50 by 50 tiles. To be fair, the monkey's map does have 6 50 by 50 regions on it. If you were to carefully fold the map, you should be able to shape it into a cube. In the example above, the 6 smaller 4x4 faces of the cube are. You will still start in the same position and with the same facing as before, but the wrapping rules are different. Now, if you would walk off the board, you would instead proceed around the cube. From the perspective of the map, this can look a little strange. In the above example, if you are at A and move to the right, you would arrive at B facing down. If you are at C and move down, you would arrive at D facing up. Walls still block your path, even if they are on a different face of the cube. If you are at E facing up, your movement is blocked by the wall marked by the arrow. Using the same method of drawing the last facing you had with an arrow on each tile, the full path taken by the above example now looks like this. Final password is still calculated from your final position and facing from the perspective of the map. In this example, the final row is 5, the final column is 7. Holy cow. Okay. Let's solve. equals in. Solve on cube false in. True. Move n steps on cube. New pos, new dir equals. Ba-da-bum. Boom, 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 boom. Ba-da. Okay. On cube, dir equals ref dir in next pos, next dir. Now facing dir.to string next dir. Pause. Dir. On cube. On cube. Do 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 do. What hard coded? Let cube side hard coded wrap. Wrap. Left wrap equals row holy shit kebabbers. Let simple wrap equals dir maze dir x y dir equals simple wrap maze X, Y, N. There. Move and steps. Okay. All right, let's still make sure everything is working still. Great. What? Cube wrap maze x y dir equals. Match. So if you're going right, let's match y divided by cube side. With zero, 1, 2. Invalid height when wrapping going off right side. So here, when we go off the right, here, let's just draw connections. New. Yeah. X. X. Okay. So if you're going off the right in the first row, let y equals let height equals y mod cube side in. Okay. So if we go off the right in 0, we're going to be doing last in row let maze with okay. I have no idea how you would solve this generally. Last in row maze. Then the height is maze height minus height let yeah. And if you're going right, then you're going to be going left. If you go off the right here, let S1 with equals 0 and let S1 then you're at S3 height. Let invert height equals so if you go off at height 1, if you go off at height 1, then you want to go in at, so height mod 4 is 1. Invert height is 4 minus 1, 3 minus 1, 2. So you want to go to S2H. Flipped height. If you go off at 1, S3 width, S3 plus flipped height. So if you are 0, 1, 2, 3, 4, 5, then your height is 5 mod 4, 1. 5 divided by cutoff side is 1. And you want to go to here. So this is height is 1. Flipped height is 4 minus 1, 3 minus 1, 2. You want to go to S3 plus flipped height. And you are going to be going down. Last in row maze, S0 plus flipped height. Left. So if you go off, then you're going to be first in call. You will be S1 plus flipped height. No, plus height. And you will be going down. If you go off the left, be going last in call maze S3 plus dir dot up, I think. Yeah, and if you go here, so it's minus flipped height, and you'll be going up. And if you go left here, you will be going to the last in call maze, S1 plus flipped height dir dot up. Because if 1, you go here, but if you're 4, you go here. Okay. Height, width, X, okay. Now it is getting tricky. So if you're going down off of all right, you're going to be going last in call maze S2 plus flipped width, and you're going to be going up. If you're in this one, you're going to be going first in row maze, S2 plus flipped width, dir dot right. Because if you're in 4, yeah. If you go down from 2, last in call maze, S0, flipped width, up. These are matching. Right? Yeah, and 3, first in row maze, S1 plus dir right. This was if you were going left off of 1. All right. So if you go up from 0 you're going to be going down in 2, first in call maze S2, flipped with dir.down. You are going to be going to first in row maze S0 plus with dir.right. If you go up from 3, you're going to be going to last in row maze S2 plus flipped with dir.left. Cube wrap. If on cube, then cube wrap maze xy dir else. I am a god. Let's go. Okay. Oh my god. $150. So it's 3 wide, 1, and 4 tall. Okay, so the shape is $50. Yes. Okay. So these are 0, 0, 1, 2, 0, 2, 3. All right, so this is A goes to A. B goes to B. A goes to A. C goes to C. D goes to D. E goes to E. And then I think this is F. Yeah. For example. Okay. So if you go off the right at 1, you will go if you go off the right at 1, you will go last in row maze S2 plus flipped height, and you will be going left. Then you'll be going last in row maze S2. Oh, and this is C. You will be going B. Last in row maze. Left. 3. You will be going last in call. Yeah. 1. Last in call. Maze S2 plus height dir dot up, and that is D. Okay, if you are going left, then you'll be going first in row maze S2 flipped height dir dot right, first in row maze S0 plus flipped height dir dot right. If you go left on 1, you will be going first in call maze S0 plus height dir dot down. If you go off 3, you will be going first in call maze S1 plus height dir dot down. That one I'm iffy about. I might have to like actually get paper out. All right, so if we're going down off of 0, first in call maze S2 plus width dir dot down. If we go down in 1, we're going to be going the last in row maze S3 plus height plus width dir dot left. And here 2, if we go down last in row maze S1 plus width dir dot left B. Yeah. And then here, if we go up in 0, we are going to be going to the first in row maze S1 height dir dot right. Okay, if we go up from 1, we're going to be going first in row maze S3 height dir dot right. And then if we do 2, so we're going up from 2, we last in call S0 plus width dir dot up G. I just hope it's right. No. Too low. All right, time to get a piece of paper. I need a piece of paper. Okay, I have a piece of paper. And now I will draw out my grid. Which looks like this. Cut this out. Okay. Okay, so now all right, A is correct. A. And then B is correct. And what about C? C is correct. And what about D? D is correct. And what about E? E does indeed match up with up there. E, so E is correct. And is F correct? Yes, F is correct. And then G. G is also correct. Okay, so my analysis here, everything is correct. So I must have messed up something here. So when we go off right 0, we want to go to the last in S2, and we will flip the height, and we will be going left. If we go off the right in 1, then we will be going to the last in col in 2 at the same height. So this is 1, this is 1, this is 4, this will be 4, and we will be going up. If we go off, if we go off the right in 2, we're going to come back in 0. Do 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 do. Oh. Let's go! Yes! All right. This one's a doozy. Yeah. This one is a doozy. Okay, so what's going on in this problem? A lot. We're given a maze. It looks like this, or a world, whatever. And we're given instructions. And basically we start up here, the first open square in the first open square in the first row, and we're facing right. And then we go 10, this means go 10, and then turn right, which is basically clockwise, then go 5, turn left, go turn clockwise, counterclockwise, go 5 more. And if we're going off in some direction, we go doo doo doo, oh no. And if you go off in some direction, you just wrap around to the other side and then show up there. Yeah, so that's what happens. And you just need to follow your path and know where you end up. So let's see, I have a square, which is either an open, a wall, or a wrap, which is something off the grid. I have a direction, which is right, down, left, or up. Direction converts to a dx dy, noting that in my grid, the origin is in the top left, so down is increasing y. That's a little confusing. And then facing value at the end, we like use the Bloopster, what's up? Thank you. No problem. We get a facing value, which is based on the direction that we're facing. If it's right, then it's 0, down if it's 1 if it's down, 2 if it's left, whatever, and that's what this is. Then we also just have a point class, whatever. Then a path element. This is what, when we rotate, we take in a direction and either counterclockwise or clockwise. And this is where I hard code in the rotations. Parsing the path is pretty simple. I just replace all the L's and the R's with L's and R's on new lines, and then I can split on each line and do it that way. L becomes counterclockwise, right becomes clockwise. Parsing the grid, it's not actually, there are no, there aren't, it's not padded with spaces, so I need to do, I create each line I create with default of spaces, and I figure out the max width, and that's pretty straightforward to create the grid of characters. Yeah, so parsing the input, just split on those separated lines, parse the maze and parse the path. So then what happens is, so we parse our input, and then to solve it, we find our starting spot, which we just, starting x, we don't know what it is. We loop through all the x positions from 0 to the width -1. If we haven't set starting x and the maze is open, then we set starting x to that. Otherwise, we don't do anything, and then we create a point out of that starting x and 0. Starting direction is right, and then we that's bizarre. So then we loop over all the elements in our path, and then if it's a move, then we move n steps in that direction. Starting from that position in that direction, we move that n steps, and then we have this on cube, which is relevant for part 2. This will give us both a new position. For part 1, we're going to be going in the same direction, but for part 2, it'll be a new direction. We update those. If it's just a rotate, we just rotate, and that's pretty straightforward. So we loop over all our path points. We get the row, which is the y +1, the column, which is the x +1, the facing value of the last direction we're facing, and then we compute this 1,000 times row +4 times column plus facing. That's the final password, and that's what we return. So how do we, rotating is pretty simple, but how do we move n steps? Move n steps. Well, we have a starting position and a starting direction, and for n times, we will get the, if we were to go in that direction, and whether we might be on a cube, if we were to go in that direction, what the next position would be and the next direction would be. If that position is open, then we move to it. But if it's a wall, we don't move to it. And basically it shouldn't be a wrap. Next in dir basically handles wrapping. So this should never return a wrap square. And then so if that next position is open, then we set position endure and go through it again. And so if we like hit a wall after one step, but we're moving 50, we're just going to keep running into the wall over and over again, because OCaml doesn't have break. And then we return our final position and direction at the end. So how do we find the next in a direction? Well, we get the xy and the dx dy, and then we take the dx dy. So if that is in range, then we check what square is there, and if it's either a point or a wall, open or a wall, then that's what we return, the point and the direction that we were going in. But if it's a wrap square, basically like this empty square, or if it's off the edge of the grid, then we're going to call wrap. And basically we have two versions of this wrap function, cube wrap and simple wrap, which will take in the maze, the starting point that we're at, or the point we were trying to get to, and then the direction that we were going. So then let's look at simple wrap. So if we were going to the right, oops. If we were going to the right from here, then we just want to get, and we're at some, like we're trying to get to some point here, xy, at this P. We're trying to go to some xy here. Well, the x is irrelevant because we're just going to be going to the first thing along this column. Or first, we're going to stay in the same row and go to the first non-empty element. So we're going to go to the first in row in the maze in the y direction. And this is going to also return the direction that we're going to be going afterwards, which, because we're doing simple wrapping, doesn't change. When we go off the left side, then we want to get the last in the row. When we go off the bottom, we want to get the first in the column on the top. And when we go off the top, we want to get the last in the column. And so the way these work is basically have this function first non-empty, where you give it your starting x and your starting y, and what direction you're going into, and how many places to check in that direction. So like the first in row, we're starting from like x is -1, row is y, and we're going right, and we're going to go try with different places. And so the first empty, we have the first non-empty, and we get the dx dy, and then for the whole length that we're going, we get our x is the starting x plus the dx and dy times the distance. If we haven't, then we match on the value of the maze at that point and the first. If we haven't set a first point and we see either a wall or we haven't set the first point and we see an open, then we set the first to that xy. Otherwise we don't do anything, and then we create that first point at the end. This can just be this. So that's how we find the first non-empty. And then it's like, to find the last in the row, we start at the just one off the right side. So the X is the width of the maze, and we're going left. Yeah. So that is that for part 1. ToString unused. Wow, so fast. Cool. So then part 2. Woo-wee! It's a cube. And so you like fold it up. Here's my cube. I folded it. I folded my cube. So now the rules are like when you go off this, if you go to the left off here, you actually start going down in this column. Crazy. Now I have no clue how you would automate detecting this and like how you could solve this for any input, because mine does not look like this. This is what mine looks like. Yeah, so this is what I did on cube. Yeah, so what I have is when you wrap, you either use cube wrap or you use simple wrap. And this was simple wrap, remember. We look at the direction that we're going, and then we just get like the first or last in each column. But now cube wrap is different. So here's cube wrap. Basically, I'm gonna hard code going off all the different sides. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different sides. Is it the same here? 1, 2. How did I mess up the counting? It should be 12. Because it's basically you just look, it's the perimeter. You just invert this, and so yeah, what? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What? How is this working? Tops A, F, G. Wait, A, B, C, D, E, F, G. Yeah, there are 14. A, F, G. Lefts, E, A, E, F. Rights. Oh my God, that's right. Okay, I was doing 3 times 4, which is the area, which should be 12, not the perimeter, which is 3 plus 4, 7 times 2. Okay, yeah. So I just hard code all 17 different cases. And so what this looks like is basically like when you go from the right here off from B, you're going to end up here. And like this, the start of this will be the 100th position. That's the cube size, because it's 50. This is 50 columns, and then this is 50 columns, and then this is 50 columns. So the first dot will be at 100. So you can use some like mod and division and mod math with the cube side to know that like, okay, if I'm going from this side B to here, then, well, to know that I'm starting from this side, I can take the height, y, divide it by the side width. If it's 0, then I'm in this one of these. If it's 1, I'm in one of these. If it's 2, I'm in these. If it's 3, I'm in these. So I take the division to know which row I'm in, like macro row, and then the mod to know what micro row I'm in, the offset within here. And then when I go over here, I'm going to go into basically the macro row 2 plus the offset. Like if I'm in the first row here, I'm going to be in the first column here. But that's, so that like, yeah, first row, same row. But for some of them, it gets flipped. Where like, if I'm going from here, from E to here, then the way these get folded, if I'm in the last, if I'm going off to the left off this last row in this section, I'm going to end up in the first row in this section going right. So I can still use my first in row, last in col, all those functions, but now which like macro row I'm in, it's going to change for each macro row that I'm in. And then the micro row or column that I'll end up in is going to be based on the div mod thing or the flipped one. And so I just like hard coded out and figured that like, okay, if you are in the first macro row, so y mod cube side is 0, then, and you're going to the right, then you're going to end up going to the left in the third row. This S2 is like an offset for the macro row. So you're going to be going to the second row plus your offset will be your flipped height, and you'll be going left. And then I just did that for each row. And it worked. And this is the same thing for the example input. And then it worked. And I only had one mistake when I copied and pasted, and I think I think like this 0 was a 2, and I was like, I don't know how I'm going to debug this. So then I got out a piece of paper and drew it out and like folded it up to make sure I was getting it right. And I did. This was the only mistake, I think. Yeah, I have no idea how you would like solve this for any sort of input. That seems like a nightmare. But someone can do it. Yeah. So that is advent of code. Day 22.